some slides that more or less are from those previous presentations. You can go ahead to the next slide, Amy. Okay, so basically when you do an internet search on injection wells, one thing will pop up is going back to 600 AD in China. I didn't want to go that far back on the history of injection wells, so I've kind of limited to the major applications of injection wells and targeting those in the United States. And starting with the first one in 1894 was the injection of heated water to dissolve subground sulfur deposits, bring it to the surface. This was done in Louisiana. By today, EPA would call this a class 3. Don't worry about the classifications. I'll have a slide on that to find those later. In 1915 was the first application of injecting gas into a depleted reservoir for storage. That was done in Canada. 1916 was the injection of brine from oil field operations, and that brine was then injected into the oil field as a form of enhanced oil recovery. And I'll speak more about the Bradford oil field shortly. In 1928, we had the injection of gas for enhanced oil recovery here in Oklahoma City field. And that's also a class 2 injection well. Go ahead to the third slide. Chronological order, continuing. 1938 was the injection of oil field brine for disposal in East Texas. And when you do a Google search on injection wells or the history of them, usually this is the first one that is usually mentioned as the first application of injection wells, or maybe the most popular one. So 1940s was the injection of fresh water to create storage caverns and basalt in Canada. And that also then extended into Northeast United States. The 1950s was the injection of fresh water to create storage caverns in domal salt. And that was performed in Texas, and that's an industry all in itself. 1951 was the injection of industrial hazardous waste. This was performed by DuPont Chemicals at their Victoria plant in Texas. And they drilled and operated 10 of these class 1 disposal wells that were disposing of hazardous waste. In 1970s, we had the injection of carbon dioxide that was used as a form of enhanced oil recovery in West Texas. And that project right there states that it's the world's largest. Then in 1970 was the injection of chemical solutions, those mentioned there on the screen, and that was injected into uranium ore deposits in South Texas, and those are class 3 wells. Let me just also note that on that item before that, in the 1970s, the injection of carbon dioxide. This slide was edited, but this is not one of those. They are labeled as class 2 wells by EPA, and at the present time, there is no desire for the operators to convert those class 2 wells as class 6, and I'll talk about that in more detail. You can go ahead to the next slide. Okay. The reason why I included this slide, this shows that in 1961, Texas had regulations that addressed injection wells. And this was probably an outcome of the hazardous injection wells that was drilled and operated by DuPont in the 1950s. And then what I have highlighted there in 1974, this is where we started to get the beginning of the federal regulations that basically came out of the Federal Safe Drinking Water Act. And this was the beginning of the UIC program. Before that, there was the Federal Clean Water Act. The Clean Water Act addressed only surface water. And then there was a need, others pressed that subsurface water, underground water needed to be protected. And that was, the reason for the 1974 Federal Safe Drinking Water Act. In Texas, on that slide, 1981, Texas Injection Well Program. Well Act was amended. It divided the regulatory authority between two agencies. And that is also true here in Oklahoma. Oklahoma has a similar policy of having the injection wells regulated by two state agencies. 1982, Texas received primacy. And what that means is that EPA in the beginning had the authority to carry out the UIC program. If a state wanted, they could petition the EPA and had to show the EPA that they had the resources such as staff, funding, they could have the same regulations, and EPA would sign off and grant that state agency to carry out the UIC program on their behalf, and that's called primacy. Next slide. Okay, just a little history about the EPA. In 1970, President Nixon, by executive order, created the EPA. In 74, Congress passed the Safe Drinking Water Act, which gave EPA the authority to regulate underground injection wells. Now, Congress first makes the environmental laws and statutes, and EPA crafts regulations. And just two sidebar notes there. As of 2020, EPA employs 17,000 employees, and the president administrator is Michael S. Regan. Next slide. Okay, two major goals of the UIC program. One is prevent contamination of underground sources of drinking water, or an acronym would be USDW, from the placement of fluids through injection wells. That is basically the holy grail of the program. And then the second is that EPA, or primacy state, regulates the permitting, construction, operation, monitoring, reporting, and closure of injection wells used for storage or disposal. Another way of saying that, they're basically looking at monitor wells and going to monitor those basically from cradle to the graveyard. Next slide.
Fred, I'm going to jump in. Is anyone else having trouble seeing the slides? We've got one person with problem.
Okay. These are some definitions that come from the EPA website. And the definition of injection well is a well into which fluids are being injected. Then you have their definition of a well, and you can see that it's pretty laborious there in text. And a well could be, simply a dug hole where the depth is greater than the width. An example of that would be a sinkhole. Or another one, a well could be that last item there, a subsurface fluid distribution system. I think that's another term for saying a septic tank or a septic, farm or system. And then definition for a fluid, it's a bit laborious also. Any material or substance which flows or moves, whether in a semi-solid, liquid, sludge, gas, or any other form or state. So a fluid could be any form of matter. It's a simple way of putting it. Next slide. Okay, here we're going to look at the definition of an underground source of drinking water. There's several items there for practicality purposes for our concern. We'll just zero in on what's highlighted there, that an underground source of drinking water contains less than 10,000 milligrams per liter of dissolved solids, or TDS. That number 10,000, how does that kind of relate or in terms of thinking exactly what is it? A little later in the bottom to the slide there, EPA secondary standard for drinking water for TDS is 500 milligrams per liter. So you can see that 500 is a number much less than 10,000. Now, the secondary standard of 500 milliliters, most of us, if we get water from a municipal uh, source, a water treatment plant, that number is going to probably be less than that. And the bottom line there, usually our drinking water from the city is somewhere between 50 to 250, either excellent or good. So the point here is that the water that is protected at 10,000 milligrams for the USDW, that is a very conservative number. And water that's usually 8 to 10,000, usually there's not any type of economic use for it, or at least for the time being. Next slide. Also, what came out of the Safe Drinking Water Act is something called a sole source aquifer. And this is defined where the aquifer supplies at least 50% of the drinking water for the service or the people that are dependent upon it. And then the item number 2, there is no reasonable, available alternative drinking water sources should the aquifer become contaminated. And there are 68 sole source aquifers in the United Nations. There's one in Oklahoma, and that's the Arbuckle Sample Aquifer. 500 square miles that services 40,000 people. In Texas, it's the Edwards Aquifer. The Edwards Aquifer was the first designated sole source aquifer. It has a area of 3,600 square miles, and it basically 2.5 million people get their drinking water from the Edwards Aquifer. In Texas, if I had a map of it, the Edwards Aquifer basically is centered over San Antonio. San Antonio doesn't have any surface water. Their water basically, or most of it comes from the Edwards Aquifer. And then that Edwards Aquifer then kind of stretches northward along I-35 up to like southern limits of city of Austin. And in Austin, they get their water from the Colorado River. So their source of water is surface, but the surrounding area of Austin, probably Austin to some degree to a smaller extent, gets some of their water from the Edwards Aquifer. Now you may say, well, what's the implications of this? Well, when you have a sole source aquifer, that could affect the land use above the aquifer. It might curtail construction. If you drive around the Austin area, you'll see green signs along the roads that say Edwards Aquifer Recharge Zone. And that area is usually where you have the Balcones Fault Zone, and the surface water, rain, runoff at the surface. When it reaches the recharge zone, it'll be intercepted by these faults, and the water will move along the fault pattern and then into the Edwards Aquifer. So that recharge zone is basically left uninhabited in terms of they've prevented construction in terms of subdivisions, apartment complexes, anything that would interfere with the percolation of groundwater on the surface down into the Edwards Aquifer. Next slide, please. Okay, we have 6 types of injection wells. Class 1 is the injection of industrial or municipal waste below a USDW. Class 2 is the injection of fluids related to oil and gas production. Class 3 is the injection of fluids for the recovery of minerals above or in a USDW. And sometimes this is referred to as in situ mining or mining in place. Class 4 is the injection of hazardous or radioactive waste into a USDW. And these wells were at one time outlawed or prohibited, but now they're only allowed where the site is, those wells are used for cleanup purposes. Class 5 is probably the largest class of wells in number. These are wells that inject or non-hazardous fluids into or a base of a USDW. And then class 6, this was added in 2010, and these are wells where the injection of carbon dioxide is below a USDW, and sort of a common term connected to these wells is carbon sequestration. Next slide, please. Hey, this is a block diagram I took off the EPA website. It's a very simple schematic, just showing, kind of a relative depths of these 4 classes of wells. You have the USDW there in the blue. That's in the middle. The geology here is probably more or less, Gulf Coast, very simple strata, alternating sands and shales. So the class 1 well there is probably, of these shown here, is the deepest well where the waste is being injected in a deep strata below the base of the USDW. The class 2, those are the wells related to oil and gas recovery, and those wells are usually just drilled below the base of USDW, and usually they're shallower than a class 1. Class 3 wells, those are the wells associated with ore bodies that are located above the USDW. And class 5 are the non-hazardous, very shallow wells, usually a few 100 feet in depth. There are some exceptions. There's one class 5 well in Texas that are thousands of feet deep. So this is a very simple schematic. Like anything, there's always exceptions to the rule. Next slide, please. So what we're going to do now is look at each of these individual classes of wells in more detail. So starting with the class 1 injection well, they dispose of industrial, hazardous, non-hazardous, and municipal waste. The waste is injected beneath the lowermost USDW. These are sometimes referred to as the deep disposal wells. There are approximately 800 operating wells nationwide. That breaks down where 53% are non-hazardous, 30% are municipal. Most of those wells come from the state of Florida, and they're associated with water treatment plants. And then 17% are hazardous. The total depth of the injection zones on these wells, and this is nationwide now, this is taken off the EPA website, varies from a shallowness of 1,100 feet to 10,000 feet in depth. On the hazardous wells, they also required to get a EPA no migration petition, and only the EPA, not a state agency that has primacy, can issue a no migration petition. And what this is that if a class 1 well operator wants to inject hazardous waste through geologic modeling, they submit their application to the EPA, and their modeling needs to show that in a time frame of 10,000 years that the injected waste will not escape out of the injection interval. And EPA reviews that, and they have the sole responsibility of issuing that. And when it's issued, then the operator can go ahead and inject that hazardous waste. If they don't get a no migration petition, they have to do something different. And looking at that diagram on the left side, that's from EPA, like all the other diagrams I have from the EPA website. And that shows, basically in relative terms, the class 1 well, and then also a class 1 well that basically represents Florida at a wastewater treatment plant. You can see that the base of the USDW is close to the base of the first string of casing, or the surface string. And the class 1 wells probably are more stringent in terms of engineering than your typical oil and gas well. And what I mean by that is that the first string of casing has to be set below the base of the USDW. And sometimes that base of the USDW, it'll vary from, site to site or the geology. Sometimes it could be thousands of feet in depth. And then when they set the casing below the base of USDW, then they're required to pump cement to surface. And I have to make, an earnest attempt to do that. If for some reason they cannot do that, and it's possible that the agency or the EPA or maybe even the operator will go ahead and, perf the casing and then, pump cement. So it's, seen at the surface. Then when it comes to the second string or the productive string of casing, that's going to be set to TD, where the waste is going to be injected. And once again, when they pump cement, it's required that they pump cement from the bottom to the surface. Okay. Let me see if I have anything else to say about that. Okay, next slide. Okay, and second is the class 2 injection wells. They inject fluids associated with oil and gas production. There are 3 types. The first type are the wells that are injecting usually, brine or water as a form of enhanced recovery wells. And that's the largest group of them. That's 79%. Then you have class 2 wells that dispose of or inject brine strictly for disposal purposes. That's 20%, and a much smaller percentage, less than 1%, are class 2 wells that have been drilled in salt, usually salt, as a form of hydrocarbon storage wells. Nationwide, there are 180,000 wells. Back to the enhanced recovery wells, that's 79%. That equates to approximately 142,000 wells. And of that 142,000 wells, 85% of them inject not brine, but they inject CO2. So that comes out to about 120,000 wells are injecting CO2 into oil and gas reservoirs for enhanced oil recovery. Keep that in mind. Next slide. Okay, I'm going to step back a little bit here, and we're going to talk about the Drake oil well. And the Drake oil well was drilled by a railroad conductor by the name of Edward Drake. Sometimes you may see the title of colonel in front of him, but that was self-imposed. He never served in the Army. And this well sparked the modern oil industry in the USA. It was the first commercial oil well in the United States. It was drilled in 1859 in Titusville, Pennsylvania. It's located along Oil Creek. There were seeps in the area, and it's probably not a bad idea to drill a well in an area like that to discover oil. The well only had a total depth of less than 70 feet, and the upper 32 feet was soil, Devonian age sandstones. The maximum production was 20 barrels per day. And like the oil industry, it was boom and bust. The price went up, and then shortly thereafter, in less than 2 years, the well was in production, then ceased and was abandoned. In that photograph there, Edward Drake is the man on the right side wearing the top hat. The oil derrick is in the background. It's covered by wooden slats, and that probably served 2 purposes. One was, I guess, during the cold winters, form of protection from the wind and the cold. And then probably more important, this was the beginning of oil derricks, and it was probably for security purposes or, basically to keep everything as secret as possible. Okay, when I was presenting this to previous time in Texas, I just want to see how Texas, compared, to this well. The first major oil field was discovered in Texas in 1894, and it was the Corsicana field in Corsicana, Texas. And the history here was the well of this oil field was discovered by mistake, not by accident, I guess you'd say. The city founders, the city hired a driller to drill a water well. And he went ahead and when he was drilling, he hit oil. And the city was not happy with that. And they refused to pay the contract of the money they said they were going to pay the driller to. But they said that we wanted water and not oil. Now, a lot of people, when they think of Texas, they think of the big oil discovery. That'd be the Spindletop that was discovered in 1901. And that well spewed oil, recorded to be 100 feet into the air for 9 years, I believe. There was peak production of 100,000 barrels of oil per day. This started the oil rush, to Spindletop. Excess amounts of wells were drilled that hurt the pressure that was pushing the oil to the surface. And the price of oil plunged at this time to an all-time low of 3 cents to a barrel. Production finally more or less ceased in the 1930s. And then the issue or the phase of sulfur production started at Spindletop. But there is still some very limited oil production at Spindletop today. You can go ahead with the next slide. Okay, factors related to oil production. When an oil field that's hasn't been drilled or production from it yet, it's estimated, generally speaking, that the reservoir is usually 75% oil, 25% water, with a small percentage of gas. When the production starts, which is referred to as primary production, only 10 to 25% of the oil in place is recovered at the surface. And then when the pressure is basically getting less and less, or toward the end of the production curve, they're usually pumping 1 barrel of oil to 10 barrels of brine. So for that type of ratio, it's kind of considered uneconomical. Then they go into a secondary production phase, if possible. And that's where they're injecting water, usually brine or fresh water, for an additional 10 to 20% recovery. And then after that, you then have tertiary production, where instead of injecting a fluid like brine, the injection of gas or CO2 or something else, or even heat or steam to recover a smaller percentage of oil. Next slide. Okay, first major water flood project in the United States, as noted on that first slide or second slide, was back in 1916. And at the Bradford oil field in Pennsylvania, they injected the brine to increase the production of oil. And Bradford turned out to be the first giant oil field in the United States. A giant oil field is noted when the production is greater than 100 million barrels of oil. As of today, Bradford has produced probably closer to 700 million barrels of oil. The schematic that you're looking at doesn't really depict the water flood project of Bradford, but the concept is there. Basically, a class 2 well will inject brine. The water then will push the oil, more toward the production wells, and that will increase production by another 10 or 20%. On that schematic showing the beam pumping unit, that is a modern day pumping unit. And that was came into existence in about 1951 by Lufkin Industries out of Texas. It's possible that back in Bradford in the early days, they probably had some kind of artificial lift, a much simpler type of pumping unit. How effective it was, I don't know. But the pumping unit that you see there and what I've read, this is the one that is the one that's still in use today. These are the ones that you see out in the field, and they came into existence in the 1950s. Next slide. Yeah, talk a little bit about the history of the Bradford oil field. And in the first phase, or the primary phase, this lasted 45 years. That the field was discovered in 1871. 10 years later, it had peak annual production. In those 10 years, it produced about 23 million barrels of oil. So at this time, it was a far cry from being a giant oil field. In 1881, the production of Bradford represented 83% of the world's oil production from 90,000 wells. In 1916, it reached its lowest daily production of 40 barrels a day. The operators there, being probably the major oil companies, felt that the field was going dry, that they got as much as they could. They abandoned the location and let the leases expire. And what is usually bad for one or someone is an opportunity for others. And if we go to the second slide. Okay, the second slide then takes us into the secondary production phase. This is where they injected brine, a so-called water flood. And this was started in 1916. And this was started by a father and son, and their names are Clayton and Forrest Dorn. You may have heard the name Forrest before. The father and son named their company Forrest Oil. Now, Forrest Oil was not a true oil company. They were not into exploration. They were strictly into providing water flood services, or back in that time, they were the first ones to apply it on a commercial scale. So what Forrest Oil did was, when the majors left, they picked up those leases. And, this goes back, quite a while ago, where things were kept, communication wasn't that rapid. And they also, tried to keep things as secretive as possible. So during the 1920s and 30s, they drilled over 1,000 wells per year, and those wells being injection wells and production wells. And they increased the production from the low of 40 to 9,300 barrels a day. And I would assume they became immensely wealthy over that. And during that production of the secondary phase, they produced probably over, that number 658, that might not be exactly correct, but it's probably close enough. They produced over 600 million barrels of oil. And as of today, Bradford is still producing oil 153 years later from when it was discovered. And the production today is probably just stripper wells. Oil production is minor, but there are a few independents that are doing okay out there. And let me say a little bit more about Forrest Oil. Okay, Forrest Oil basically then, took this technology of water flooding when the Bradford field was, basically on its last legs. They went into Illinois and applied the same thing. They're very successful there. And then they also took their operations into Oklahoma in 1935 and 1930s, around there. They started the so-called first beginning of commercial water flooding, and made more money doing water flooding. But then everyone else kind of caught on to what they were doing. The majors realized that, hey, they could do the same thing. And then you also had service companies that were competing with Forest Oil to do the same type of service to water flood. So in the 1950s, Forest Oil's main focus was on exploration, and water flooding being in secondary. And in the 1950s to the end, they expanded operations into 15 states of the United States. They also established production in Canada, South America, and the Middle East. Forest Oil was also the first and only independent to drill an offshore well, offshore Louisiana, when those leases were available. And when it was all said and done, Forest Oil left a major mark in the oil industry, and that ended in the year 2014, when Sabine Oil and Gas basically bought them out. The name of Forest Oil has been dropped, but Forest Oil had a major presence at one time in Oklahoma. Next, please. Okay, this is taken from EPA years 2020. These are the number of Class 2 injection wells in operation. And by just looking at that, you can see that Texas is number one, has approximately somewhere between those two numbers, say 50,000 Class 2 wells, followed by California, 29,000. Kansas, 16,000 plus, Oklahoma, 10,000, Illinois, over 7,000. And these numbers, I said before, represent present operating wells. If you look at Pennsylvania, Pennsylvania has 1,861. There's possibility that there was a lot more Class 2 wells, but those Class 2 wells over time were plugged and abandoned. So if there was a number that was like total number of Class 2 wells drilled, yeah, these numbers would change, and especially for Pennsylvania and Ohio, those numbers would probably be, quite a bit larger there. Next slide. Okay, another example or an application of a Class 2 well is to inject fresh water to dissolve salt to create caverns. And in 1915, gas was injected into a depleted reservoir in Ontario, Canada. I guess the only reason why I mentioned that slide that you're looking at there, I took that off the internet from the company KBB, and they're one of the leading companies in creating or drilling salt caverns and salt domes. And on that slide there on the far left side, it shows a depleted reservoir. So it looks like those wells are injecting gas into a depleted reservoir for storage. And then when needed, they'll take that gas out, maybe like during the winter time, and then, provide it to the market. So in the 1940s, there were storage caverns that were created. There's over 1,000 caverns in the United States. The majority of them, or 700 of these caverns, are in Texas. Of the 700 caverns, the majority of them, or 414, are drilled and created in salt domes. And those salt domes are usually located along the Gulf Coast of Texas onshore. The bedded salt caverns in Texas are found in West Texas. There are approximately 500 domes along the Gulf Coast. 84 domes are in Texas, and this is all onshore now. And of those 84 domes in Texas, 18 have have caverns, and once again, of those 18 separate salt domes, they have a total of 414 domes. Looking at the slide, these caverns can hold or store temporarily hydrogen, compressed air, brine, crude oil, natural gas. And there's quite a bit of technology behind this. Basically, they'll drill a pilot hole into the salt. They'll inject the fresh water to dissolve the salt, bring it to the surface, and then they'll run in there with a survey, some type of sonar device, and get a 3D image of it. And they can create these caverns with a fine engineering technique where when it comes to the shape and the volume, they have good control of that. It's almost like, directional drilling. Next slide, please. Good example of these storage caverns is the Strategic Petroleum Reserve. If you were old enough where you remember the 1970s, we had the Arab oil embargo, and that was in 1973 and 74. And what resulted from the Arab oil embargo, Congress created the Strategic Petroleum Reserve, which is a form of emergency fuel supply. Looking at the diagram there are 4 of these Strategic Petroleum Reserve facilities in the United States. 2 are in Texas and 2 are in Louisiana. In Texas, starting from the left, the facilities are there in the red square, Bryan Mound, Big Hill. Then you go into Louisiana, you have West Hackberry and the one in Baton Rouge. There's a total of 62 caverns. The maximum capacity of these caverns is 727 million barrels of crude. As of today, the caverns have approximately 371 million barrels of oil, so they're about 50% occupied. Now, that other item there underneath says the equivalent of 46 days of import protection of 2024. The way I interpret that to be is that it would take 46 days to import oil to fill the cavern. And I don't know if that means fill the cavern when it's totally empty or to fill the cavern with the amount of oil it has in 2024. That I'm not sure about. That's 727 million barrels of crude of oil. Just check this on the website. One website stated that the U.S. consumes 20 million barrels of crude daily. So 20 into 727, that gives you approximately 36 days. The original intent of the Strategic Petroleum Reserve is that it was only to be used in true emergencies, things such as war, a hurricane. Now it's become somewhat of a political issue sometimes where they've drawn on the oil to so-called lower the price of gas, but that's probably more of a mental thing than an actuality. Another thing to keep in mind with the Strategic Reserve is that the oil that's in the caverns is crude oil. So in order to actually use that crude oil, they have to pump out the crude oil. That takes time. Then they have to transport it to a refinery. That takes time. To process it, that takes time, to a finished product. And then to send that finished product to the market, whatever that market is during an emergency, that takes time. And you add all those time segments up, and I've seen a figure where it says it can be like 35 days. So the Strategic Petroleum Reserve is almost like a Band-Aid a little bit. It's not to be, it doesn't have the inventory for a considerable amount of time when the oil transport is interrupted. Next slide. Okay, we'll go to the third class, the class 3 injection wells. These are the wells that inject fluids, dissolve minerals that are in the USDW. Some of these minerals are ore deposits, so uranium, sulfur, sodium sulfate, salt, and copper. There's 18,500 of these wells nationwide, representing 165 sites throughout the United States. And the mining sites require from EPA, only EPA can issue this, an aquifer exemption. And the reason for that is that, these ore bodies are located in a USDW, and the USDW is to be protected by so-called all measures. But when you have mining sites, you can get an exemption where you kind of carve out a small area of the mined area, and the operator, has, by modeling or whatever, will show that the mining operations and the fluids will only stay within that small area and will not migrate out into the outside of the aquifer and contaminate it. Next slide. Okay, in Texas, these class 3 wells have been used to recover the following minerals, and one of the more popular ones that's going on today is uranium. But before uranium, there was quite a bit of sulfur production. Next slide. Okay, I just want to throw this in here. This map showing the salt deposits. Bedded salt is in the lighter shade. The domal salt is in the orange, and you can see that the domal salt is basically just limited to the Gulf Coast. And usually domal salt is a treasure chest for natural resources. It has oil and gas production. It has sulfur. We'll talk about it a little bit later. And uranium is usually associated with these areas. Next slide. Okay, another example of class 3 injection wells is to recover sulfur. And this was performed in 1895 in Louisiana, where the German-born chemist Hermann Frosch injected superheated water into a salt dome, which would then dissolve the salt, and then the liquid salt would then, come to the surface. And in that schematic on the right side, a production well, an injection well is almost one of the same. It has 3 strings of casing. 2 strings are used for injection purposes. One to inject the steam. Another one is to inject the air for create a high pressure at the bottom there. And then one of those strings, when the sulfur is melted to a liquid, then it'll come with the aid of the pressure, air pressure, come to the surface. And that schematic there on the left side of a salt dome, that's somewhat of a classic representation of it. In reality, it's not that simple. And the sulfur is located or found on the top of the salt dome in the caprock. In 1929 to 1930, there was production of sulfur at the Bowling Salt Dome in Texas, which is located in Wharton County. That dome produced, or that mine produced over 89 million long tons of sulfur from 8,000 wells. And at that time, this was the second largest sulfur mine in the world. Okay, next slide. Another application for class 3 wells is used to extract uranium. And uranium is found in several parts of the United States. I should also say that uranium production, even at its peak, and then and the peak for the time being is behind us. United States has never had large reserves of uranium. We've been kind of like a small-time player. There's like 5 countries in the world that produce the bulk of the uranium. And uranium in the United States, especially here in Texas, it was found by accident. And what I mean by that is that in the 1940s, the reconnaissance in the oil and gas industry was gravity airborne surveys, not seismic. And in one of these airborne surveys that they were performing along the Gulf Coast, and the primary target was to discover and map salt domes that were below the surface with gravity. Salt has a very low gravity value, and the sediments around it, the value is higher. And when they were flying across, they also came across some anomalies, and these anomalies had very high gravity values, just the opposite of salt. So when they got back on the land, when the plane landed, and probably a day or two later, they went out there where these high anomalies were. Those anomalies were created by uranium that was at the surface. This goes back to the 1940s. Well, in the 1940s, the U.S. government was also in the midst of the nuclear arms race, and they needed a supply of uranium for atomic weapons. So the federal government was funding companies to explore and recover uranium. And some of the oil and gas companies like Exxon, Mobil, Arco, Conoco, probably some others I haven't mentioned, they also had mineral divisions. So they were the first round of players, especially in South Texas, to explore for oil and gas there. So somehow, can you go back to the other slide? I just need to kind of wrap this up a little bit, go a little bit faster. So basically, 1940s, the uranium was, for nuclear weapons. When you had the fall of Russia and the end of the nuclear weapons program, the uranium that today is basically goes to nuclear reactors to generate uranium. Okay, next. Okay, this is an example of what a uranium mine looks like in Texas. The green is the ore body. That represents 15 feet of economic thickness of the uranium. It's 250 feet wide, and the length there is 10,000 feet long. The green shaded area is 55 acres of production area. The operating or the mining area is that outer ring that encompasses 244 acres. In that green ore body, they have drilled 464 of these class 3 wells. And the class 3 wells, they inject some type of lixiviant. Basically, it's fresh water with some type of additive. It dissolves the uranium. Then the uranium is then pushed, or more or less intercepted by a production well, comes to the surface and is recovered. And let me see what else. Okay, class 4. Okay, class 4, these are the wells in 1984 were banned by EPA, but now they're only authorized for groundwater cleanup actions. These wells are shallow. They usually, inject into the USDW. 434 wells nationwide at 32 sites. Next one. Okay, class 5. This is probably the largest class of wells. These are the real shallow wells, usually just a few hundred feet deep. They inject non-hazardous fluids into a USDW, and what they're injecting supposedly does not degrade the USD in any form, and usually that is based a lot of times solely on TDS. Okay, there are 650,000 of these wells nationwide. There are 23 types. These wells are used for groundwater remediation, aquifer recharge, sometimes experimental projects, stormwater drainage. I'm not going to talk about anything more about the class 5 wells. Next one. Okay, this is the one that's I found to be a little bit more interesting. This class 6 wells is the latest class of wells. They are a new addition in 2011. They inject the carbon dioxide, CO2, in a deep rock formation. And this information comes from right from the EPA website, just like the diagram. There are 47 wells nationwide, and that follows. California has 16, LA 15, Illinois 10, Indiana 3. It says Texas has 1, but I think that is a mistake. I think that was a class 5 well that was used for purposes of injecting CO2 and then monitoring the CO2, see if it stayed within the reservoir there. So looking at the class 5 well diagram there, it shows that the facility there is a coal-fired power plant, where the source is coal. It's emitting a lot of CO2, and that CO2 will somehow be captured and then sent to a class 6 well to be injected into a deep formation. And a lot of times this is called CO2 sequestration. And let me see, next slide? Yeah. Let's go back. Okay. Let's go back to the other slide. This one is not my revised slide right here. On the class 6 wells, basically they were a outcome of global warming. And as you can remember, global warming, some government officials and some experts have stated that global warming is one of the biggest threats to the United States in terms of, sea level rising. And to reverse global warming, which they attribute to excessive amounts of CO2 being emitted, they wanted to reverse this, so they came up with carbon sequestration, where the excessive amount of CO2 that's emitted from a power plant or a factory would then be captured and then permanently disposed of. Okay, so that was the intent of the class 6 wells, just like that diagram shows. Okay, next slide. Hey, this is a map taken from EPA that shows the breakdown of EPA and primacy states. Some states, if they want to, they have petitioned and were granted the primacy where they carry out the UIC program. Some states on their own have decided they want primacy of all the states, or they can also choose to have primacy for a few states. For class 6 wells, the wells that have primacy is North Dakota, Wyoming, and Louisiana. Texas has submitted their application. It hasn't been granted yet. Next slide. Okay, this is an inventory of UIC class wells broken down by the states of Oklahoma, Texas, and nationwide. So on class 1, Oklahoma has 5 wells, or maybe 4. I've seen some publications say it's 4 wells. Those wells in Oklahoma, they're non-hazardous, and they're usually located along Interstate 44 in the central part of the state. Texas has 108 wells nationwide. It's 800. The majority of the class 1 wells are in Florida, and it's those wells that are specific to the waste treatment industry. That second item with the asterisks, those are no migration petitions. These are not wells, but sites. that have injection wells that dispose of hazardous waste. Obviously, Oklahoma has none. They don't have any class 1 injection wells that dispose of hazardous waste. Texas has 23 sites. Now, those are sites, not wells, like the um, DuPont facility in Victoria, Texas. That one site had, at one time, 10 hazardous wells. And Texas has about 50% of the nationwide sites, being 43. For class 2, these are the wells associated with oil and gas. Oklahoma, over 10,000. Texas, 52,000 plus. Nationwide, 180,000. Texas has about 1/3 of the total number. Class 3, Oklahoma 0, Texas 4,600, and nationwide there's 18,500. So Texas has about 20% of the wells, somewhere around there. Class 4, Oklahoma has 30, Texas 106, nationwide 434. 5, 20, those are the non-hazardous shallow wells. Almost 3,000 for Oklahoma, 57,000 for Texas, and 650,000 nationwide. On class 6, Oklahoma at the present time, there are no permits issued. Texas, that number should be 0. Nationwide is 47. Now, getting back to the class 6 wells, something associated with it, the U.S. government, to jumpstart carbon emissions, since late 1990s, they have basically distributed over $30 billion to research and start pilot projects with companies, industries to address this. And besides that, they've also came out with credits, 45Q tax credit for carbon sequestration. This is basically where CO2 emissions is treated as a commodity. And there are almost like stock markets where companies are given credits where they can buy and sell these credits to offset their CO2 emissions. One company, if you have a lot of credits, like what I've seen recently, Tesla, they had accumulated over $9 billion of credits related to their battery manufacturing facility. That $9,000 of credits, they can then sell those credits to companies that are producing too much emissions. So that company will buy those credits from Tesla. Also, to, I guess, somewhat encourage low CO2 emissions, you have electric cars, and the federal rebate has been extended on electric cars, where, depending upon the price and some other conditions, the consumer gets a $7,500 rebate from the federal government. And that, getting back to Tesla, that $9 billion of credits they had, that goes into their annual reporting, and some of the profit that they're reporting is a lot of times due to the amount of credits that they have. These credits have also been extended into the timber industry. Trees absorb CO2. That's a form of capture. And the federal regulations have also included that the timber industries and some timber farms up to 40 acres, they can also qualify for credits. And another instance, another example of this credits, and it'll be less one I'll talk about, one major oil company that needed to buy credits because they had excessive amounts of CO2, they were purchasing large tracts of timberland, of timber. So they were using those credits from their timber to offset the negative aspect of their facility. So I guess my point here is that if you're interested in, class 6, and it's more than just, capture and then disposal, because most of the CO2 today is going to enhance oil recovery, and they're making plenty of money just, producing oil. It's if you do a Google search on it, you'll find that there's a lot of aspects to CO2 sequestration, especially with class 6 wells. A lot of parts of the United States, the geology does not support drilling a injection well there. Any kind of class 6, any type of deep injection well. So the injection wells right now for CO2 most of them are in the Gulf Coast, and most of that CO2 since the 1970s is going, to the oil fields to enhance oil production. And that is about it. I think next slide. I think that should be the end. And if anyone has any questions, I'll be happy to entertain them.
We've got a few comments on the chat. One about the National Academy of Sciences in 2013, talking about induced seismicity potential with CO2 sequestration. From Bert Fisher, and then Heather Holm also said that there are not 47 class 6 wells permitted nationwide. That might be the number of applications currently submitted. And then there's another mention that there's 43 class 6 applications in Texas right now.
Right. Let me just make a comment there. I worked for a state agency as a permit writer for 29 years, and there is a big difference between submitting an application, getting a permit issued, and then using that permit to actually drill a well. So I have seen over time that a lot of times the operators have submitted an application, the permits were granted, give it to them, and whatever the reason is, they decided not to drill the well. So the number that I would zero in on are actual wells drilled, and that number is usually much smaller than the number of permits issued, and that number is smaller than applications.
We were running kind of long. Do we have any other questions out there? All right, I'll let everybody go then, I think. We've also had a request for the slides, so I'll get you in touch with them, Fred. Okay. Everyone, just to be aware, we are recording these, and we will have those available in our archives. I'll try and get that done and get some emails out with that. We have a bunch of thank yous and great presentation.
Thank you.
So thank you everyone for joining us. Thank you, Fred, for sharing your knowledge, and we'll see everyone again soon.
Okay, bye now.